IT Kanpur. So this is the lecture 5 of your thermodynamic course, and it is expanded isothermally. Okay, this is expanded isothermally against an external pressure. And what is the pressure? 180 until the pressure of the gas becomes 180. Calculate the amount of work in expansion in joules. So we have to calculate work done in expansion in which unit? In joules. Okay, so we have to calculate this. Okay, so we have given V1 initial volume, that is 2 liters. Okay, we don't know the final volume, and the pressure initially was 5 atmosphere pressure. So P1 was 5 atm, and against an external pressure of 1 atm until the pressure of the gas becomes 1 atm. That means final pressure will become 180. That means P2 will your P2 will become 180. We all know that this is an isothermal condition, and for an isothermal condition we know that PV is equal to constant. How? Let me tell you. We know that PV equal to nRT. Okay, so if your N is number of moles, so number of moles are constant. Okay, and R is your gas constant. So this is also a constant value. Okay, this will not change. These values will not change. So now this is temperature. In case of isothermal condition, here the condition is isothermal. So in case of isothermal, that means temperature is constant. For isothermal, so your T is constant for isothermal process. So if your N, R, T, all three values are constant, then your PV will also be constant. Okay, so if N, R, and T, that is temperature, is constant, then the multiple of pressure and volume will also be constant. Okay, so now your PV is constant. That means if P1 and V1 is the initial condition and they are going under change, and this is the final condition where the pressure is P2 and volume is V2. Then if it doesn't change, that means P1 into V1 will be equal to P2 into V2, because they are the multiplication of PV is a constant value. Okay. So now we have P1 V1 equal to P2 V2. We know the value of P1, P2, V1, but now we can find the value of V2 from here. Okay. So let us substitute these values in this equation 1. We will get P1 is 5 atm and V1 is 2 liters. Okay, equal to P2 is your 1 atm and V2 is what we have to calculate. Then this will become V2 equal to 5 to the 10 of 10 liters. 10, let me tell you, 5 to the 10 into atm into liters divided by 1 atm. Okay, we have just bring this over here because in here it was in multiplication, then it comes inside if you want in division. So this atm and atm, now we have V2 equal to 10 liters. So now we have V2 in our hand. So let us calculate the work. Okay. So in order to calculate work, so what we know, the formula of work. So work is nothing minus V external dV. And dV is here V2 minus V1. Okay. So let us calculate now. V external was, that means it was expanded against P external is here 180. Okay, so external pressure P is 180. So P external 180. Let us put this value over here into V2 was, we have calculated over here 10 liters minus V1 was 2 liters. Okay, so minus 1 atm into 10 minus 2 is 8 liters. Okay, so what do we have? 8 liter atm. So in last class, I've told you in order to convert this liter atm into your joule, we have to multiply this with 101.3. So let us multiply this with 101.3. 1.3. So this will give us values in joule. So what is multiplication of this? This is minus 810.4 in joules. So the amount of work done in expansion in joule is 810.4. So solution is the amount work equal to 810.4 joules. This is our answer. Okay, this was the answer for this problem. So now we have solved many problems. Let us move further, and here in this session I'll introduce you with the term enthalpy. So then I'll start uh, deriving the relation between your enthalpy and internal energy. Then we will move further and we will learn what is molar heat capacity and what is the relation between molar heat capacity at constant volume and constant pressure, and we will derive equation and get a relation between them. So let us start with the enthalpy. So as mentioned here, the enthalpy H, which is denoted by H, is the thermodynamic property of a system. So like internal energy, enthalpy is also a thermodynamic property of a system. Okay, so and it is defined as the sum of the internal energy. Okay, we will take the sum of the internal energy of the system and then the product of the pressure and volume of the system. That is nothing but the energy of the system. So the enthalpy, that means enthalpy is sum of the internal energy and the pressure volume and the multiplication of the pressure and volume. Okay, this is what is called enthalpy. And we know that enthalpy is denoted by H, internal energy is denoted by U, and P is your pressure and V is your volume. Then we get the equation of enthalpy, that is H equal to U plus P, which is nothing but the sum of the internal energy and the product of the pressure and volume. That is nothing but the energy of the system. So mathematically, it is the heat contained in the system measured at constant pressure. So this is nothing but the measure heat at constant pressure, heat content of a system at constant pressure, then we will call it as a cell. So let us take the system. System calculate the heat content at a constant pressure, then it will give you the enthalpy of this. Okay. So it is nothing if we have to measure at it at a constant pressure. I have told you earlier that the internal energy was nothing but the heat absorbed at constant volume. Okay, so here enthalpy is heat contained at a constant pressure. In case of internal energy, it is volume, and in case of enthalpy, it is your pressure. Okay, your pressure will be constant, and in case of internal energy, your volume was constant. Okay? This is the basic difference. So now we have our equation where we have H equal to U plus PV, but it is impossible to determine the absolute value of enthalpy. Okay, this is the absolute value of enthalpy. So it is impossible to determine it. So we will, but it is possible to determine the change. Okay, so we will calculate the change in the enthalpy. So enthalpy. So we can calculate. I'll write it over here, but we can calculate change in enthalpy. That is nothing but delta H. Why? Because it is impossible to determine the absolute enthalpy, absolute value of enthalpy. Okay. So enthalpy is a, now let us see what is written here, that enthalpy is a state function. Why? See, here enthalpy in this equation, enthalpy is equal to U and sum of U and PV. So your internal energy is a state function. Okay, this is state function. Okay, your pressure and volume. Your pressure is also an state function. Okay, pressure is also a state function. Okay, your pressure is also a state function. So now this your temperature, pressure, and internal energy are state function. Then if we are taking their sum, then which gives you enthalpy, then it will also be a state function. Okay, so enthalpy is nothing but state function. This is very important. If this is state function, what it means that we can add them or subtract them. Okay, that's why we can calculate the change in enthalpy. So it is expressed as a change in enthalpy. I told you earlier that it is expressed in the form of change, and which is represented as delta H over here for a process between initial and final states. And this is very important. I told you that enthalpy is measured at constant pressure. Okay, so this is very important that it is measured at a constant pressure for a process between initial and final state. Okay. Also, enthalpy is an extensive property. Let me write it over here that enthalpy is an extensive property because your energy, that is P, T, and U are extensive property. Okay, so this is also important that if your enthalpy is an extensive property, that means we can add them or subtract them because in equation these are also an extensive property. Next, if now we have to calculate the change, that is delta H. So this is equal to nothing but the heat supplied at a constant pressure, which I told you earlier that this is the heat contained at a constant pressure of a system. So this is the heat supplied at a constant pressure to a system where as long as the system does no additional work. Because if it does the additional work, then we will have to add that. Okay. So this is nothing but change in enthalpy is equal to the heat supplied at constant pressure. So heat, what is heat? Q. Heat is denoted by Q, and if it is at constant pressure, then we denote it like this. So the change in enthalpy is denoted by delta H. Then it gives you delta H is equal to heat supplied at constant pressure, that is QP. So we denote it like this, QP. For an endothermic reaction, okay, if your reaction is endothermic, that means in that case your heat will be absorbed by the system from the surrounding. Okay, so if your system is taking heat from the surrounding, then it temperature will increase. That means the heat will increase. Okay, if heat increases, that means your value of Q, because the system is absorbing the heat here, so your value of Q will be greater than 0. That means it will be positive. So here, if your Q is positive at constant, let's say it is at constant pressure, then if it is positive, then your delta H is equal to QP. If your QP is positive, then your delta H will also be positive. So this implies that your delta H, that means change in enthalpy, for an endothermic reaction, I have denoted it with endo, will also be positive, because your heat absorbed is also positive. So this implies delta H endo will be a positive value for an endothermic reaction. Okay? And what if the reaction is exothermic? That means your heat will be evolved from the system and it will be given out to the surrounding. That means if your heat is being taken out from your system, that means your heat content is decreasing. So if in this case your Q will be less than 0, because it is getting out of the your system. Okay, so in that case your heat is getting evolved from the system. So that means your heat at constant pressure will be less than 0. That means QP will be negative. And if this is the case, what will be your delta H? That means delta H exo will also be a negative value. Okay, that this implies that change in enthalpy change in enthalpy for a reaction, if the reaction is exothermic, it will be negative. So here, in conclusion, if the reaction is endothermic, then your delta H will be positive, and if your reaction is uh, exothermic, then your delta H will be negative. Okay, so this is what is the basic of the enthalpy. So let us move to the next slide. So here we will derive the relationship between the enthalpy and the internal energy. Okay. So let us start this derivation. So we will, this is the relationship between the enthalpy H and the internal energy Q. Let us consider a system at a constant pressure, and it undergoes changes from an initial state having the thermodynamic terms H1, Q1 and V1 to final state S2, U2 and V2. Okay, so let us consider a system. Here it was H1, U1 and V1. This is initial state. Initially, this system is having enthalpy of this H1, internal energy U1 and volume V1. Then it undergoes change, and then it becomes the enthalpy, internal energy and volume changes, and it becomes S2, U2 and V2 respectively. So this is the final state of the system. It is going under a change. So what will be the change in enthalpy? Change in enthalpy. So change in enthalpy is nothing but the enthalpy of the final state minus the enthalpy of the initial state. So enthalpy of the final state minus the enthalpy of the initial state. So this is what we do. Okay. So the difference we get will give us the change in enthalpy. This is nothing but delta H equal to S2 minus H1. Because change in enthalpy is delta H, enthalpy of your final state is H2, and enthalpy of your initial state is H1. Okay. Now we have delta H is equal to S2 minus H1. We know that H is equal to U plus PV. Here I have told you that enthalpy is nothing but the sum of the internal energy and the product of the pressure and volume. So if your H is U plus PV, then for initial state, in initial state, your H is H1, U is U1, and volume is V1. So if we substitute these values in this equation, okay, what we will get? The enthalpy of the initial state, that is H1 as internal energy of initial state plus this P into V1, because initially volume was your V1. And similarly for the final state, your H2 will be U2 plus P into V2. Okay, now we have get the values of H1 and H2, that means the enthalpy of the final and initial and final state. So what we have to calculate? The change in enthalpy. So in order to calculate the change in enthalpy, we will substitute the values of H2 and H1 from here to this equation. Okay. So let us put this. Let us calculate now. So your first I will erase. Okay, I will take a new slide. Okay. Just wait a second. So because we have to derive this, so we need a new slide. So I'll just take the pointer. So we have where we delta S is equal to H2 minus H1. So we have delta H H2 minus H1. We have H2 equal to U2 plus PV2 and H1 U1 plus PV1. Let substituting this value, these values of H1 and H2 in the above equation, what we will get? Delta H, that is change in enthalpy, is equal to H2 is U2 plus PV2 minus H1 is nothing but U1 plus PV1. So let us expand this. This will become minus U1 minus P into V1. Let us put the values of internal energies together, U2 minus U1, and the pressure volumes together, PV2 minus PV1. So here P is constant, we will take it out. So U2 minus P1 plus P into V2 minus P1. So U2 minus U1 is nothing but the change in internal energy, which is denoted by delta U, and plus P into, similarly V2 minus V1, that is change in volume, which is nothing but delta V. So this is what we get. Change in enthalpy is equal to the sum of the change in internal energy and the pressure volume work at constant pressure. Okay. This is calculated at constant pressure. Here what we have substituted, U2 minus U1 as delta U and V2 minus V1 as delta V. That is, this is change in internal energy. Sorry, change in internal energy, and this is change in volume. Okay, so this is what we get. Delta S is equal to delta U plus P delta V. So we can calculate the change in enthalpy by using this equation, using its relationship with this internal energy and volume. Okay, so we have calculated here that delta S is nothing but delta U plus P delta V. Here it is written that as this is the relationship, okay, between the enthalpy and the internal. The first law of thermodynamics, we know that delta U, that is change in internal energy, is nothing but the sum of the heat and work. Okay, so let us substitute this value in this equation. What we will get here? It was delta H delta U plus P delta V. This was the equation. Let us just, this was equation 3. Okay, this is your equation 3. Okay, substituting the value of delta U, that is Q plus W, from first law of thermodynamics. What we will get? We will get delta H is equal to Q plus W plus P delta V. Okay, so we also know that work is nothing but the minus P delta V. Now let us substitute the value of W over here. What we will get? Delta H equal to Q plus W is nothing but minus P delta V. Okay, so we are substituting over in this equation. Okay? So Q plus W is minus P delta V, and here we had plus P delta V equal to. So this will become Q minus, plus minus will become minus, minus P delta V plus P delta V. So these are same value. Okay, so we will cross this because this will give us 0. So here your delta H will become Q, and we are calculating it at constant pressure. That means it is Q at. So this gives you equation 4, which is written over here. That is the heat absorbed at constant pressure, because here Q is nothing but heat and P is nothing but pressure. So the heat absorbed at constant pressure, that is Qp, is, it is nothing but the heat content. Okay, heat content of the system. So heat content of the system at a constant pressure is nothing but your change in enthalpy. So I have already written over here that yeah, it was mentioned over here that the change in enthalpy is equal to the heat supplied at a constant pressure. So this is what we have now, that delta H is equal to Q P in equation mathematical form. Okay? Mathematical. So let us consider now. Let us consider a closed system. Okay, so this a system which is closed. So this is a closed system. Okay, and it contains gases. Okay, okay, and if these gases react together to form products which are also gaseous, Okay, and this is happening at a constant pressure, constant temperature and pressure. So this is isothermal, as well as if temperature if it is constant, then it is a thermal, and if pressure is constant, then that is isobaric. Okay, we all know that. So we have condition of isothermal and as well as the isobaric, where your temperature and pressure both are constant. Okay, so a reaction is happening between gases, and they are forming products which is also gaseous, and this is occurring at a constant temperature and pressure. And let's say its initial volume was Vi, and the final volume is Vf. I denotes initial and F denotes final. Okay, so Vi and Vf as the total volumes of the reactant and product gases respectively. And let us take the number of moles of the gaseous reactants as Ni, and the number of moles of the gaseous product as Nf. Okay, so number of moles of the reactants, the number of moles of reactants, that is the initial number of moles, and the NF as the basically the number of moles of the product. Okay, so we know that PV is okay, so this is the PV. We know that PV is equal to nRT. Okay, if PV is nRT, then for initial state, that means for reactants, uh, your pressure is constant, your temperature is constant. So, and your pressure, temperature is constant, R is a gas constant, so this is also constant. So what will be changing? Your value of the volume and the number of the moles. Okay, so initial, that means initially what was volume? Vi. Okay, so we will write P into Vi. Okay, P into Vi. That is equal to N. Initially the number of moles were Ni, so we will write Ni and R and T as such, because they are not getting filled. Similarly, for products, that means for the final state, your this equation will become P final volume Vf, P into Vf is equal to moles of the products, that is Nf into RT. Okay, so this is what you get for the initial and final state. Okay, so let us subtract these values, subtract the final state uh, to the initial state. What we will get? So this is nothing but the final state minus the initial state. Okay, so let us subtract these values. So this was, it will become P into Vs minus P into Vi will become equal to NFRT minus Ni into RT. Okay, so if we take P common from here, it will become Vf into Vi, because P is constant, because initially they have mentioned that the pressure and temperature is constant. Okay, so here RT is also constant, so let us take this RT out of it. So it will become Nf minus Ni into RT, which is nothing but this equation. Okay, so we have got this equation by subtracting this 2, this 6 minus 5. Okay, 6 minus 5. So now we have calculated this, and we know that Vf minus Vi is nothing but Vf minus Vi is nothing but the delta V. That means change in volume. How the volume is getting changed between the final and initial state. And similarly, Nf minus Ni, because in this case it is gaseous, the products are gaseous, then so Nf minus Ni will be changing number of moles, but we will write it as B, because as the products are gaseous over here. So this is what we have. So we have NF minus NIS delta NG and VF minus VIS delta V. So let us put these values in this equation. What will we get? P into VF minus VI as a delta V. So P into delta V equal to NF minus NIS delta NG and then into RT. This is, we substitute this, we will get this equation. Okay, as a P into delta V is equal to delta NG into RT. Now we have the value of P delta V as a delta Ng into RT, then we know that change in enthalpy is nothing but delta U plus P delta V. Okay, so if we know the value of delta U and we know the value of P delta V, then your enthalpy, change in enthalpy can be calculated. Now we, for this system, we have already calculated the value of P delta V. Now we can substitute this value in this equation to get the change in enthalpy. Let us substitute this value of P delta V. Substituting the value of P delta V in this equation, what we get? Delta H equal to delta U plus P delta V is nothing but delta Ng into RT. So this is what you will get. Okay. So in order to calculate the change in enthalpy, you can and you know the change in number of moles and you just know the, if you know the change in number of moles, the temperature and the change in internal energy, you can definitely calculate your enthalpy. Okay. So this is the same relation between your delta H, that is internal energy or enthalpy, change in enthalpy, and delta U, that is change in internal energy. Okay. So this is now in hand we have this much. H is equal to U plus PV. Then we have this delta H is equal to delta U plus P delta V. We have this much equation because we need to remember this. Okay. Delta H equal to U plus P delta V because the pressure is constant. Okay. Next we had delta H, nothing but Q at constant pressure. Heat, heat, heat content of a system at constant pressure. And in last we have calculated that delta H is nothing but delta U plus delta Ng RT. Okay. So you must remember all these equations because it will help you in solving many issues. So this is all four equations. Let me see if we have any equations. No. So these are all the four equations that you need to remember. So now let us move to the next part where so this uh, so enthalpy changes for different types of reaction and okay. So why we are calculating the change in enthalpy? Because for different types of reaction and phase transition, so enthalpy changes. Okay. For different types of reaction and phase transitions, your enthalpy changes. So if enthalpy is getting changed, so we need to calculate the change in enthalpy. Change in enthalpy of the particular reaction. Okay. What is standard heat of formation? The standard heat of formation, that is a compound getting formed. So if a compound is getting formed, then what is it? standard heat of formation. So, so the standard heat of formation of a compound is defined as the change in enthalpy. Okay, again the change in enthalpy. Because if a compound is getting formed, that means reaction is happening. Okay, so if there is a reaction, then there will be the change in enthalpy, and then thus we will have to calculate. So the change in enthalpy that takes place when 1 mole of compound is formed. Okay, so if 1 mole of compound is getting formed from its elements and they are present in their standard state. Standard state means at a 298 Kelvin temperature and 1 bar pressure. So, so the standard heat of formation, let me define it again, that the standard heat of formation of a compound is nothing but the change in enthalpy that takes place when your 1 mole of compound is getting formed from its elements present in their standard state. Okay? And by convention, the standard heat of formation of all elements is assigned a value of 0. Okay? So this is very important because the standard heat of formation of all the elements is assigned as 0. Also, this is very important point I would like to mention over here, that the standard heat of formation, that is delta H naught F, is equal to 0 for diatomic elements. So, what are diatomic elements? For example, the standard heat of formation is equal to 0 for hydrogen gas, nitrogen gas, oxygen gas, fluorine, bromine, and iodine gases. For these, your standard heat of formation, that is denoted by delta HF naught to denote the standard, it is 0 for diatomic element. Okay, so this is 0 for these gases. So here they have given the standard heat of formation of iron sulfide. So here for iron, the standard heat of formation will be, for iron sulfide, here they have given the standard heat of formation as minus 100.42 kilojoule per mole. And the standard heat of formation of this acetylene gas is plus of 222.36. Okay, so these values are given in kilojoule per mole. Okay, so this is nothing but the unit of enthalpy. Okay, these are given in kilojoule per mole. Next, they have given the heat of formation of HCl gas, which is nothing but delta H F naught equal to minus of 19.4 kilojoule per mole. So in this table, the standard heat of formation of some of the compounds are given. Here it is for water, it is minus 242 kilojoules per mole. For HCl gas, it is minus 92.4 as shown over here. For HBr gas, it is minus 36.4. For ammonia gas, it is minus 6.1. And for carbon dioxide gas, minus 95. Similarly, for methane, it is minus 74.85 and so on. Okay, so this is basically the table for standard heat of formation. Okay, this is the table. So let us move to the next slide. So this is what are thermochemical equations. So we are going to solve problems on the to calculate the change in enthalpy. Okay, where we will be asked to calculate the change in enthalpy. So in order to calculate that, we will have to know some basic rules that how to balance chemical equation, because in order to calculate your enthalpy of reaction, you must balance the thermochemical equation must be balanced. Okay, so, otherwise we will get error in our calculation and our answer will be wrong. So what are thermochemical equations? So a thermochemical equation is a balanced stoichiometric chemical equation that includes the enthalpy. Okay. So this convention must be adopted for a thermochemical equation. So what are these? These are first the coefficients in a balanced thermochemical equations refer to number of moles of reactants and products involved in the reaction. So let us take a reaction. It's getting converted into. So A and B are your reactants. Okay. C and D are your products, which are donated in capital letter. Your A, B, C, and D. These are number of moles of what? Of your reactants and products. Okay, and products. Okay. So here they are saying that the coefficient in a balanced thermochemical equation refer to a number of moles and reactants and of moles of the reactants and products involved in the reaction. So here, if your A, B are reactants, then what will be the number of moles of reactants? That will be A and B. So here, A and B are number of moles of reactants, and C and D, they are number of moles in product. Okay, so this chemical equation must be balanced. Okay, the enthalpy. Next, we have the enthalpy change of a reaction. That means delta HR. For it is denoted by delta HR. That is R denotes reaction over here. Has to be specified with appropriate sign and unit. Okay, as I mentioned earlier that the unit of delta HR is nothing but it can be in kilojoule per mole or whatever they ask. We will have to calculate in that rate, and also the sign. If delta HR of a reaction is positive, we will have to mention that it is a positive. Positive means it is endothermic reaction. Okay, and if your delta HR is negative, that means it is an exothermic reaction. Okay, so this is very important thing that you must remember. So the enthalpy change of a reaction has to be specified with the appropriate time, that is over here, and unit, that is joule per mole or kilojoule per mole. Okay. Next, we have if the chemical reaction is reversed. So what will be the change in the value of delta H? Your it will be nothing, but the sign of your delta H will be changed. The magnitude will remain same, but its sign will get changed. Let's say initially for reaction A to B, your delta H was plus of 81.4 kilojoules per mole. So now, if we have to calculate the delta H for the reaction B undergoing conversion to A. So what will be your delta H now? Delta H will be nothing, but here the sign will get reversed. That if it was positive, then it will become negative. That means negative of the magnitude. That means the value will remain same. That is minus of 1.4 kilojoule per mole. So this this is a tree we have studied till now. So in next class, I uh, will teach you all the other necessary conditions in order to balance the thermochemical equation or to get the correct thermochemical equations for the enthalpy change. This is what we will learn more about. These are all the things we will learn in the next class, and then we will solve some questions. Okay. Uh, but for now, let us. I'll end this session. Okay. Uh, Thank you.